Hello, and welcome to the X-56 Scaled Composite Research Testbed Final Presentation, sponsored by the Air Force Office of Scientific Research and mentored by Dr. Herman Fazil. We are the UAX-56 team. The aviation industry today has the goal to design increasingly efficient aircraft. High aspect ratio composite wings are often more flexible than conventional ones and react to external stimulations with greater deformation. A combination of external factors can lead to flutter and other dangerous flight states. The goal of our project is to design and manufacture a 1 to 4.5 dynamically scaled X-56A airplane, originally built by Lockheed Martin to serve as a research testbed to study the effect of structural motion on the boundary layer transition and separation. This project will provide future engineers an insight to safely design high aspect ratio flexible wings using composite technologies. To begin each flight test, the X-56 will be placed on the runway. Once the pre-takeoff checklist has been completed, the pilot will apply full power and begin the takeoff roll. The aircraft should take off from a paved surface in order to minimize the damage from foreign object debris. As the drone approaches its rotation speed, the pilot will apply slight back pressure to the transmitter joystick to make the airplane lift off. The airplane will start climbing, and as it reaches 100 feet, the pilot will slightly reduce power to conserve battery. Once it reaches an altitude of 300 feet, the airplane will begin to look for traffic in any areas of turbulence. After clearing the area, the drone will loiter for about 8 minutes to collect data. During the data collection portion of the flight, the aircraft will utilize its onboard sensors such as accelerometers, bending sensors, and an FPV camera for the team to understand the effects of structural motion on the boundary layer transition and separation. Lastly, the aircraft will reduce power and return to base for landing. The total planned mission time is around 10 to 12 minutes.
The initial project proposal included the construction of a 1/6 scale model. However, the chosen internals did not fit within the fuselage, and as a result, a change to a 1 to 4.5 scale model was presented. This was the smallest scale possible that would allow the construction of the half-span model to fit inside the U-Arizona subsonic wind tunnels test section. Shown here is the Solidworks model of the 1 to 4.5 scale X-56A aircraft. The aircraft is constructed with a fiberglass skin and includes 2 LiPo batteries with EDF engines conducting the propulsion system. These EDFs are supported within the fuselage by engine mounts shown here. Similarly, the internals, including the flight control system, will be supported by an instrument plate. The wing structure includes 3/4 inch foam ribs and telescoping carbon spars that allow for varying wing flexibility. The design also features winglets to reduce wingtip vortices. The aircraft also includes a tricycle-style landing gear formation and various other support systems, such as balsa ribs and spar holders contained within the fuselage. Access panels are included to provide easy access to the internals. Here is a full 360-degree view of the X-56A model.
This year's team created a non-modular design through the use of a one-piece mold. The benefit of this design was faster manufacturing, ultimately leading to more flight testing in the allotted time. The only downside to this marvelous design is it weighs 250 pounds, requiring at least a team of 4 to move it or to mate it.
To ensure our model does not bond to the molds are first waxed and buffed, then coated with a spray-on application of PVA. The skin of the aircraft is constructed using a fiberglass and epoxy resin laminate containing aeromat core that runs through the center of the wing and fuselage sections for additional stiffness. It's determined to have 2 2-ounce layers of fiberglass on the exterior and 1 3.2-ounce layer on the interior. The exterior of the skin is made from gel coat to provide a smoother wetted surface in flight.
In order to mate the 2 halves of the one-piece mold, the team used microballoons and epoxy. Prior to mating, the larger internal structures are placed inside the fuselage, and all central structural supports are secured in place. Diamond pins in 4 key locations are also utilized to inhibit movements in the mold during the mating process.
Due to the interruption of COVID-19 and loss of access to school facilities such as the Composites Lab and Machine Shop, the new deliverables are as follows. To switch our focus to the half-scale model and complete an aerodynamic analysis as well as calculations through the use of X-Flyer. We are additionally tasked to design fuselage and wing molds.
To understand the performance of the half-scale model, aerodynamic analysis was performed utilizing X-Flyer simulations. From this, the aerodynamic coefficients were obtained and other relevant aerodynamic properties, such as the neutral point, were determined. Additional new deliverables included calculating a new center of gravity with fuel burn considerations, as well as a power analysis for the new scale engine choice. This information will prove insightful for future research concerning this project.
The differences between the molds of our original and updated scaling are minor. The half-scale molds have separate sections for the fuselage and wings, creating a modular design. The plugs are to be male, to which an original layup will be done and removed, creating new female molds made entirely out of fiberglass.
The results of the half-scale model mirror those of the 1 to 4.5 scale model aerodynamically. The neutral point placement was determined to be about 67% of the fuselage length, with a static margin of between 5 to 10%. When determining the CG of the half-scale model, fuel burn from the tanks must be considered. As fuel is being burned, the CG moves further forward, increasing the static margin, however not increasing it beyond the 10% safety threshold.
Although we were unable to gather physical data, our results were still useful to our mentor and sponsors. In order to verify our design, a prototype was created. A 1/10 scale model was manufactured from a smaller scale mold using our original design. After routing the molds and doing test layups, we determined our mold design to be feasible. Prior to spring break, the team put in over 200 man-hours to prepare our molds for layups. This ensured we had a near-perfect polish for our state-of-the-art composite shells. Before the pandemic started, the team was able to complete one half of the aircraft. While the design and hard work of making the molds was completed, the aircraft will stay grounded and unfinished for the time being.
Overall, we believe that this project and its results will be of use to future engineers focusing on structural motion in boundary layer transition and separation. We would like to take this time to thank our sponsors, the Air Force Office of Scientific Research and Dr. Herman Fosel, as well as a shout out to Michael Mearsman and Jacob Hamas for their hard work and dedication to our project.